Hi, my name is Anjana Iyer, and this is Lab 5, Magnetic Braking with Faraday. So the purpose of this lab is to observe Faraday's law experimentally with a magnet falling through a tube of aluminum foil, and then we want to model it computationally and compare the results to the experiment. In a preview of the results, the time it took for the magnet to fall through the tube was 1.25 seconds, and then computationally it was 1.32 seconds. And the magnetic force from the metal tube caused the magnet to fall slower than if it was normal free fall. Some physics principles that are important in this lab are magnetic flux, and that's shown here with the integral of B dot n, which is the normal vector, dA, and then Faraday's law, where EMF is going to equal the negative derivative of flux, and then Lenz's law, where negative in Faraday's law, nature abhors a change in magnetic flux, and magnetic field of induced current works to counteract the external changing magnetic field. We also want to discuss the Biot-Savart law, and it's just the magnetic field of a dipole, and then Ohm's law, which is I equals EMF over R, and then the magnetic force on a current-carrying wire, which is going to be F equals I times the change in length crossed with the external magnetic field. Newton's third law is also used for every force as an equal and opposite force, and then Newton's second law, and all of that is shown below. For the experimental model, there's a drawing on the right, and the system is going to be the bar magnet, and the surroundings are the aluminum foil roll, earth, and everything else. The initial conditions, the initial velocity of the magnet was from rest, so 0 meters per second. And then of the tube, the length was 0.3 meters, the outer radius was 0.15, and the inner radius was 0.025. The magnetic dipole moment was 1.4 amperes times meters squared. And then for the experimental model, here's some of the data. The time for each trial, it was approximately 1.25. And then here is the computational part of the experiment. And for the first part of this code, I inputted the data that I collected about the tube and the magnet, including the width, length, radius, the inner and outer, and then mass and the dipole moment. And then at the bottom, the magnetic field due to the dipole is calculated there. At the top of this code, the flux is calculated, and then the magnetic force on the magnet is also calculated, and then the currents that are produced are also found here. Here, the B field is computed at each ring, and then I calculated the magnetic force on the magnet. And then I updated the magnet's velocity and position accordingly. And in conclusion, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicated current flowing in opposite directions, and which color corresponds to clockwise current and which counterclockwise. The red was counterclockwise and blue was clockwise. And then if we were to flip the magnet around, the system's dynamics would not change because the orientation of the poles don't matter. And then the total time in tube compared to the computational system, they're going to be slightly different, but the computational system is probably more accurate by creating more rings. And then what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Beginning and end, the velocity graph was steeper as force of gravity acted more, and the middle is more stable as the forces of gravity and magnetism were balanced. Dropping a magnet through a metal tube also slows its descent as the magnetic force from the tube counteracts the gravitational force, and then the magnetic force comes from Faraday's law, inducing a current in the tube. And some error that could have occurred during this lab was, or could be in measuring the time that it takes for the magnet to fall and neglecting air resistance. What if the resistivity of the conductor were reduced as close as possible to 0? The induced current value would increase, increasing the magnetic force and slowing the descent of the magnet. And what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes would disrupt the current flow, decreasing the current and magnetic force, speeding up the magnet's descent.